step will be introduction of our very prominent speaker in the field of quantum diamond, quantum science, and quantum technologies, Professor Fedor Jelezko. Fedor is currently a director of the Institute of Quantum Optics at Ulm University and fellow of the Center of Integrated Quantum Science and Technology. His research interests are at the intersection of fundamental quantum science and quantum technologies. His research team is exploring applications of spin qubits in diamond for information processing, communication, sensing, and imaging. For his achievements in the field of quantum science, Fedor has received several honors, including Walter Schottky Prize of the German Physical Society, Zeiss Research Award, Spolsky-Rebane-Personov Medal, and State Research Award of Baden-Württemberg. Fedor, the stage is yours.
Yeah, thank you very much, Olga. And first of all, thank you for organizing these lectures. It's very exciting events to have speakers on nanodiamonds in your application. It's a pleasure to be here. And my topic today will be applications of qubits in diamonds for quantum technologies. I will start with stating that NV centers in diamond and diamond as a platform was rapidly developing into area of research in very different quantum science and technology fields. It is a platform for solid-state quantum optics. Nowadays, small diamond resonators with color centers are considered to be among best platforms for quantum repeaters elements. We are trying to build quantum computers based on spin qubits in diamond, where color centers are interacting under control to create large-scale entangled states. And this is the field where not only academic groups now active, but also companies are starting to take over. And the third area is quantum sensing and imaging. And I think in this area, maybe applications will come at first. For quantum sensors, you need only a few qubits to get a regime where sensors can be advantage to use compared to classical centers. And this is maybe the area where the first real-world applications will come. Maybe not in quantum computing or simulators for next 3 years, but in quantum sensors, we are already, in some cases, can show that coherent control of a few qubits can already be of very big importance, very attractive for use them in a variety of sensing applications. Today I'm going to show how nanodiamonds, spin qubits and nanodiamonds can be used for sensing magnetic fields, with particular focus on applications in NMR and EPR at nanoscale, but I will also touch a bit the topic of medical imaging using nanodiamonds. But first, I would like to introduce spin qubit in diamond. So qubit is...
I want to make sure, are you sharing maybe some
slides?
Oh,
sorry. Yes. yes
no, you're
I apologize. Yeah, I somehow missed sharing this.
Worries.
Yeah. Thank you for your comment. So let me see what I would share this. Okay, I hope you can see the screen.
Yeah, perfect. Looks great.
Perfect. Yeah, you see the full screen, right, Maud?
Yes.
Okay. Yeah. So spin qubit in diamond. So today I will mostly talk about qubit associated with nitrogen vacancy color centers, For most of you, they are already known, but very short introduction. This is a color center which consists of a nitrogen at carbon position in diamond lattice and vacancy nearby. It forms 6 electron systems, which combines very interesting optical and spin properties. In fact, for this color center, spin state is coupled to optical transition, allowing to initialize and read out spins of individual color centers. When excited with laser and promoted from a ground to excited triplet state, center undergoes spin selective shelving into a metastable singlet state, and this singlet state decays always to one of the spin transition with magnetic quantum number as ms equals 0. And this spin selective shelving into singlet state leads to 2 important effects. It allows you to polarize spin of NV center in one particular sublevel of the ground state triplet. And it also leads to the fact that the brightness of fluorescence, a number of photons emitted by a color center, depends on the spin state. ms equal plus and minus 1 states, because they're shelved into a singlet state, they have efficiently lower quantum yield. So the fluorescence intensity associated with emission from these states is lower compared to ms equal 0 state. So if you shine the light, excite color centers, and record fluorescence emitted by color center, the response on the laser excitation will be different for ms equal minus plus 1 state, which is shown here in the dark, in the black, compared to a red line corresponding to emission from ms equals 0 state. So this is 2 important ingredients for a qubit. You need to be able to initialize your system in well-defined state. We do it via optical pumping. And you need to be able to read out the state, and that can be done by measuring fluorescence. And this is quite sensitive technique. Experiments can be done on the level of single color centers. Also, I need to say that we don't collect typically all the photons, so experiments typically are done not in a single shot. And in order to read out the state of a single NV center, you need about 100 times repetition. So we are basically not projecting every time by measuring NV center. So we need a few excitation cycles to detect it spin states. Experiments I'm going to discuss today are done mostly in a microscope, combining optical detection, allowing to measure single color centers, and capability to manipulate spins using microwaves. So we excite color center in a confocal microscope. We use avalanche photodiode with very high detection efficiency. And often we are also checking whether we are dealing with a single NV center by measuring fluorescence autocorrelation function. It shows the anti-bunching on photons feature, which correspond to emission corresponding to fluorescence of a single quantum emitter. So this feature, kind of anti-bunching on a photon in time, is a signature that you deal with a single color center. We combine optical microscopy and optical spectroscopy with magnetic resonance. In our case, microwave antenna is pretty simple. It's a flat microwave structure on diamond. And when we scan the microwave frequency and reach the resonance between spin transitions in the ground state, we can observe the magnetic resonance using optical detection via measuring fluorescence intensity of the color center. Actually, conversion of NV center from ms equal 0 state, which is bright, to ms equal plus minus 1 state by microwave irradiation leads to decrease of about 30% in fluorescence intensity. And this contrast is used in all these measurements I'm going to show later on most of the measurements I'm going to show later on, for sensing applications. Actually, we can do more than just observe magnetic resonance. We can also coherently control spins. And here I show you the picture of the Rabi oscillations, where by applying short microwave pulses, we can drive the spin from eigenstate or coherent superposition and then to another eigenstate. And so we can coherently control spins and create coherent state of spins, which is very essential for quantum technologies. On the left side, you see a typical picture for a single NV detection experiments in magnetic resonance, in this case in bulk diamond, with this microwave antenna deposited on diamond, but very similar setup, very similar microwave structures are used in nanodiamonds experiment. So the presentation today will be about sensing. Owing to limited time, I will not catch on quantum computing or simulations. And in talking about sensing, I will give you three parts of sensing story. First, talking about resolution and dynamic range of quantum sensors, protocols very quickly. Then I will show you how we can apply color centers for measuring magnetic resonance in nanoscales, but also will show you how you can sense radicals and temperature inside of cells using nanodiamonds. And at the very end, I will also show you how diamond particles can be used for enhanced magnetic resonance imaging. And I will start with sensing in general, how to make out of spins a magnetometer. Well, this is pretty straightforward. If you can detect spin transitions, and if you can measure frequency of the spin transitions, say frequency is dependent on the magnetic field. So spins levels will evolve in the magnetic fields. And if you know magnetic dipole moment of your electron spin of NV center, you can, by measuring the frequency, the energy separation between spin sublevels, you can calculate the magnetic field. So if you measure the frequency, you can get magnetic fields with high precision. How precise depends on the sharpness of the transition. The sharper is the spin transition, the better is precision of determining the frequency. And so this is very intuitive. You can also formulate it more precisely. What is the precision of measuring the magnetic field? So you can then define absolute limit in the precision. And for sensors based on coherence, this smallest possible magnetic field you can measure is related to a smallest possible phase you can measure when spin precess after excitation of coherent state. And the smallest possible magnetic field depend on the atomic parameter of NV center, so essentially magnetic moment, and then a number of NV centers, measurement time tau, and coherence time big T. In many experiments I'm going to talk today, we are using a single NV center, so this number is fixed to be 1. And then the only parameters which defines the precision per square root of measurement time is coherence time. The longer you can accumulate the phase, the longer is your coherence time, the better is your sensor, the higher sensitivity you can reach in your magnetometry. And for color centers in diamond, and diamond here is a unique material, I need to say, the coherence time is very long, especially if you compare to other systems under ambient condition. Here I give you example of precision of the single NV center spin recorded at room temperature, and it stays there, the phase for up to 300-400 microseconds. So this is quite long time for spin systems. And you can now take in this formula, calculate the precision limits. It's very close to what we observe, and it's a few nanotesla per square root of measurement time per NV center. You can compare this sensor with other available magnetometry approaches. And I plot here the benchmark picture from a review article by Christian Degen. And it has two benchmarks for magnetometers. One is sensitivity, shown here as x-axis, and another is kind of a size of the sensor or possible separation of sensor to the object you would like to measure. The best sensor will be somewhere here, having a high spatial resolution and high sensitivity. But currently available sensors are lying somewhere in this region, squids, Hall sensors, and color centers in diamond are already now reaching the sensitivity limit capable to detect a single electron spin or single nuclear spins. They reach the size of a few tens of nanometers and have the sensitivity of a few tens of nanotesla. This is when we are talking about a single NV center. If you take many NV centers, you can increase the sensitivity. There are demonstrations already on a picotesla scale, but then the sensor itself becomes larger, and I'm going to talk more about nanoscale sensing today. Now, what are examples of application? One is to measure magnetic signals of biomolecules. The system, NV center, can operate as a quantum sensor at room temperature. And one example of applications of this magnetometer at nanoscale is detection of nuclear spins of single protein molecules. This is a picture from a work by Mikhail Lukin and collaborators where protein was attached to a bulk diamond. So this is not nanodiamond demonstration. And precession of nuclear spins was detected by diamond magnetometers. Diamond NV center was implanted just a few nanometers below the diamond surface, and so then we turn it in a spectrum analyzer settings, and the spectra associated with precession of hydrogen and carbon present in protein were detected on a single molecule level. Those spectra are maybe not very spectacular. They are noisy, and it took a few hours to detect them, but the gain in sensitivity compared to conventional nuclear magnetic resonance was many orders of magnitude. So it was the first demonstration of detection of a single molecule NMR, and conventional nuclear magnetic resonance required billions and billions of molecules. Those spectra are, of course, noisy. They don't have yet very high spectral resolution. And the main goal in the field of nanoscale NMR, single molecule NMR, is essentially to reach the performance of conventional nuclear magnetic resonance, where one can detect very highly resolved spectra, and based on this tiny shift of spectral lines and understanding of interactions inside of molecules to reconstruct three-dimensional structure of unknown molecules to measure dynamics. And for this, both the spectral resolution need to be improved and the sensitivity need to be improved. In terms of spectral resolution, so currently the demonstrations using NV centers on a very small number of molecules allow you to separate different elements which are building the molecule. So we can distinguish between hydrogen and carbon, as you have seen. One can even detect chemical shift using advanced spectroscopy technique. But what is still to do is to detect the tiny spectral features associated with J-coupling and nuclear Overhauser effect. And this is now a developing story, how this NV nanoscale NMR can reach this limit and how it can reach the same performance and maturity what was already done for conventional nuclear magnetic resonance, which is a golden standard in biochemistry and biology studies. Now I basically give you a few more examples of quantum sensing measurements that can be useful. Diamond magnetometers can be not only interesting for NMR. It can detect magnetic fields associated with other important processes in cells. For example, if you have an open membrane channel, there is a current which can reach picoamperes flowing through these channels. And if you place sensor close to this channel, the associated magnetic field will be on the order of a fraction of a nanotesla. So kind of within reach for a single NV center. Catalytic enzymes might have paramagnetic spins inside of enzyme, and activity of enzyme is leaving a magnetic impact near the enzyme. And if you are just 10 nanometers apart associated with this electron spin, magnetic field is on the order of a microtesla, well within a reach for single NV center magnetometers. You can think also about detecting activity of neuron cells. When action potential propagates through the neuron, there is a current flowing through. And if your sensor can be brought very close to the cell, at a few tens of nanometer distance, associated magnetic fields can be quite high. Initial estimate were on the order of 100 nanotesla. More pessimistic estimates are in a picotesla range, but it's still within a range of sensitivity of NV center magnetometer. In order to make these measurements possible, it's very essential to interface diamond with biological systems. You have seen examples of detection of molecules on glass, kind of in solution, but in principle, we would love to make measurements inside of living cells to detect metabolic processes. And here there can be two ways to do this. One is to interface bulk diamond with NV centers implanted very close to the surface with cells. That would allow you to measure processes very close to the interface, maybe diamond membranes, membrane channels. And so this is one of the avenues where many groups are active, and there are nice demonstrations of sensing layers near the surface of bulk diamond with very shallow NV centers that are placed inside of this diamond. And so this is a very promising avenue. But the other avenue, which allow you to look inside of cell, is to use nanodiamond, where now NV center is located inside of particles with, again, short distance between surface of diamond and NV center. If these nanodiamonds are functionalized, it can be taken by cells, and then the whole sensing scenario can be transformed inside of cell with much more potential. So you can functionalize nanodiamonds with molecules that target certain proteins, and you can target certain processes inside of the cells. And this will be avenue I'm going to now show you. But first, so we need to create these particles with NV center, and we need to make sure that NV centers in diamond particles behave similarly to NV centers in bulk diamond. And so the production of diamond particles is very essential fields. Diamonds can be grown in a variety of techniques, high pressure, high temperature, or CVD. They can be milled to small diamond particles, and the nitrogen present inside of diamond can be converted to NV center form by first electron irradiation of diamond, creating vacancies, and then annealing, leading to migration of vacancy and association of vacancies with nitrogen forming NV center. And this you can follow here in this picture, like evolution of color from a yellow color associated with P1 centers to greenish color. This is where you have many of GR1 vacancies, and then to this pink color associated with NV center. So efficient conversion from a nitrogen to NV center is very important step, and there are many efforts to do this conversion important. So it's also important to monitor conversion during this irradiation by electrons and subsequent annealing. Here I show you our recent results, which is a collaboration with Purion and Leibniz Institute for Surface Engineering. We have irradiated 1B type diamond with electrons at different doses. And what was important in this work, that irradiation was done at high temperature. That's allowed to avoid aggregation of vacancies and damage in diamond, and conversion efficiencies from P1 to NV was quite high. We can monitor this conversion efficiency by measuring EPR spectra of diamond. This is example of EPR spectra where this very broad feature is associated with NV, not the sharp lines. This is because of anisotropy of EPR owing to presence of zero field splitting in nanodiamonds. And what you see here, these features and growth of this line part is associated with appearance of NV center. We can quantify this NV concentration by measuring intensity of EPR line, and we have then measured the number of NV centers created by electron irradiation under this high temperature irradiation condition for different sizes of nanodiamonds provided by Purion. We have seen that for 2 micron particles and 100 micron particles, we can reach conversion efficiencies up to 20%. So I'm talking about conversion from P1 concentration to reached NV concentration. Interestingly, for very small particles, about 25 nanometers, we have reached conversion efficiency of about 60%. It's a bit surprising. So the absolute concentration of NV, however, is lower, and this conversion of above 50%, you expect 50% because usually you need one P1 center to form NV and another P1 center to donate electron to form negatively charged NV center. We think that this above 50% level of conversion might be related to the fact that in small particles, not all the nitrogen is present in P1 form. Some of nitrogen is not EPR active, but still can participate in forming NV centers. So this is basically a very good result. So you can convert roughly all the nitrogen that you have in particles to NV form. Of course, you still need electron donors, and that means also that very small particles, a few nanometer, can already have NV centers, can be used for sensing because in the small particles, they are very close to the interface. They can be taken by cells. So this is very promising results. Now, of course, particles themselves need to be brought to the form where they can be useful for sensing. They need to be isolated, taken in a solution. And it is often so that nanodiamonds tend to aggregate, especially if they have sp2 shell on top of this. And there is an effort of community essentially to clean nanodiamonds, make their surface to be hydrophilic, or coat nanodiamonds by functional groups or functional materials that lead to colloidal stability of diamond particles. And this is a very important step. In some cases, you like to target certain biomolecules inside of cells via creating functional groups on top of diamonds. And there are several strategies how to do this. Either taking a diamond from your synthesis and irradiation and then creating functional groups on a diamond surface directly, covalently bound functional groups, can be amino groups or other groups. If you have a chemistry that is tuned to these functional groups, so you can potentially target biomolecules already with this type of nanodiamonds with a covalent shell of functional group. There is also another approach where you take a biopolymers, which is folded around nanodiamonds, and this biopolymers can be loosely bound to diamond particles but provide you a large number of functionalities which can be chemically created, and this is another avenue of functionalization. There is also a third avenue to create a hybrid particles with a core to be a nanodiamond, but the shell is a quartz, and there is a rich developed chemistry on top of quartz for bioapplications. This can be another avenue of functionalization. All these avenues are currently explored, and there are pluses and minuses in each of them. If you are using covalently bound functional groups, usually you don't add so much size to your particles. If you create a shell around your particles, so the particles became larger, and there are some limitations associated with this. Nevertheless, so all these areas are under development, and it was also shown that you can transport these nanodiamond particles inside of living cells. And because magnetic resonance experiments can be performed under ambient condition, you can also do all the detection of magnetic resonance that I have shown before. An example of a bulk diamond on diamond particles, and here is example of Lloyd-Hollenberg publication where a cell, a HeLa cell, was deposited on a glass, and single NV centers and single nanoparticles were detected. You could also apply a microwave drive to the spin and drive Rabi oscillations you have seen already before. And now the Rabi oscillations or coherent state of NV-cent and diamond nanoparticles now feel the magnetic fields from the environment, and there is metabolic processes inside of cells. Magnetic fields are associated with spins created inside of cells, and now the coherence time can be used now as a sensor. So coherence time is very fragile, and it can be used as a marker for sensing the environment. So you can transform all this machinery that was developed in terms of application in quantum optics now for biosensing inside of cells. I give you a few examples also what you can sense. It's not always experiments inside of cells. Some of them are on the glass, but here is example how T2 time and T1 time are changing if you bring radicals inside of cells. And here is, for example, the histogram of T1 time for pure nanodiamonds without adding radicals. And if you add radicals in your environment, you produce a chemical reaction leading to production of radicals. The T1 time, relaxation time of spin changes, and this can be used as a marker for chemical processes in the vicinity of nanodiamonds. You can also make precise measurements using these techniques. This is an example where we have varied the concentration of radicals, and we have followed the evolution of relaxation time of spins as a function of concentration of radicals. And so this is now interesting tool for detecting environment of your spin using decoherence of a single color center as a signal. Usually decoherence is a bad thing in quantum technologies, but here decoherence coming from environment that you are interested in is a signal for your measurements. And in terms of number of spins, it's very sensitive technique. So if few spins in the 10 nanometer environment can be already detected. So in terms of number of spins, this technique holds the absolute limit in EPR measurements. In terms of concentration, one needs to be cautious because NV center only detects spins in a very close vicinity. So in terms of concentration, this is not a record value, but in terms of the number of detected spins, because you are sensitive only to a few nanometers volume, it's definitely one of the most sensitive available techniques. Now, the spins and radicals are not the only species that can be detected using spins. I can now show you a few recent developments in novel functionalities One is the temperature sensing using spins, and temperature sensing in biology is very important field. Many processes in cells are regulated by temperature or can be influenced by temperature. And currently, for in-cell studies, not damaging cells, the golden standard of temperature measurements is fluorescence thermometry. Some dyes change intensity of fluorescence lifetime associated with this change in intensity as a function of temperature. And there were examples of measurements of temperature gradients inside of cells by a few Kelvin. But then this measurements basically initiated discussion in a community. And according to thermodynamic model of the cell, the gradients of temperature inside of cells cannot be larger than a millikelvin if you take into account energy produced by the cell. Of course, in a tissue, in a large number of cells, you can reach much higher variation of temperature. But on a single cell level, the model, our understanding of thermodynamics predicts a very small variation of temperature. And that's why it's very important to have sensors that are artifact-free. And it's believed that fluorescence thermometry is not always artifact-free because fluorescence of dye can be affected not only by temperature, but also by other parameters, for example, by change in pH. And here, the color centers in diamond can play a role. Magnetic resonance line of color centers are temperature sensitive for in V-center case. In principle, the spin itself, the spin half system, is not temperature sensitive. It only reacts on magnetic field, but for in V-center, because it consists of at least two electrons forming the spin, spin 1, these two electrons interact, and so the zero field splitting, the offset in EPR frequencies is related to confinement of the wave function of in V-center. When diamond lattice compresses, it brings electrons to closer contacts, and that means that the zero field splitting increases. So this frequency of EPR transitions of in V-center now is temperature dependent. So that's not very good news for quantum computing applications. So I need to stabilize temperature to avoid this drift, but it can be accessed for temperature measurements. And here I show you the change of the frequency of in V-center spin transition as a function of temperature. So it's about 80 kilohertz per degree Celsius, and that converts to sensitivity for the best in V-centers and a single in V-center level to about 5 millikelvin for 1 second measurement time. So that's already a very good sensor in terms of sensitivity, but most important, it's very calibrated sensor. So it don't react on any other parameters. It's essentially only follows the compression of diamond lattice. And so this technique of measuring temperature by measuring zero field splitting of in V-center was also brought to applications. I show you here a collaboration with Tanja Weil Group at Max Planck Institute in Mainz, where we have coated nanodiamonds with phototoxic drug. And at the same time, we have attached some very small heating elements. So when laser light was exciting these nanodiamonds, it induces the heating of the element responsible for activation of the drug. And we have basically followed this by measuring the temperature, by measuring ODMR of in V-center. And at the same time, we have been measuring toxicity of the drug. And we have seen the correlation between temperature rise in the vicinity of nanodiamonds or in nanodiamond and activity of the drug inside of cell. So that's basically nice combination. So you can transport the drug inside of cell, you can activate the drug, and you can follow its activity by measuring temperature using in V-center transitions, spectral response. you can also basically do this in much more simple way. Previous experiments I was showing require microwave and pretty complex magnetic resonance experiment. Some color centers in diamond show shift of the optical transition as a response of temperature. The mechanism is the same. Optical transition can be affected by compression of diamond lattice because wave function of electron get kind of compressed. For optical transition of silicon vacancy center, we have frequency shift of about 1% of the line width per degree Celsius, but now it's optical transition shift, and this gives you a sensitivity of about 0.3 degrees Celsius per 1 second measurement time. It's not as sensitive as ODMI. There the transitions are much sharper, but it's much simpler to realize. You don't need any microwave, it's just optical microscope, and this is also an interesting avenue to apply. So that was also applied inside of cell. It's another piece of work in collaboration with Tanya Weil, where we have inserted nanodiamonds now doped with silicon vacancy centers. And we have been able to follow diffusion of nanodiamonds inside of cell and combine this with the temperature measurements via shift of the optical transition of silicon vacancy centers. All right, and now I think I very quickly come to the last part of my presentation, another application of nanodiamonds, now not for optical or DMR sensing, but more for improving another imaging technique, very important in medicine, magnetic resonance imaging. So the main idea is to use nanodiamonds doped with carbon-13 nuclear spins as a label for a very high sensitivity MRI. So the enhancement and sensitivity is coming from the optical pumping of NV center by light. So we produce nanodiamonds doped with carbon-13, which produces NMR signal, but we polarize this carbon-13 by polarization transfer from optically pumped NV centers to the nuclear spin. Remember, you can polarize NV center to well-defined state, so you could cool efficiently the electron state of NV center with light, and now you have two spin systems. One spin system is nuclear spins, which are relevant for MRI imaging. Another spin system is electron spin of NV center, which is fully polarized, and you can transfer polarization. You can transfer the entropy from one system to another. This can be done by special protocols. We drive the NV center electron with Rabi frequency matching Larmor frequency in nuclear spins. And in this case, these spins can flip-flop, and so you kind of heat NV center electron spin. You cool NV center nuclear spins. You can create very, very cold system of nuclear spins for crystal spin at room temperature, but spin temperature is very low. And so here's example of improvement of signal of NV center inside of bulk diamond by this protocol. So the red curve is a very noisy C13 signal related to thermal polarization, and the blue curve is enhanced signal by this hyperpolarization protocol. And you can even bring this all the way to imaging. This is the image of this diamond inside of MRI scanner done by my colleague Volker Rasche from Ulm University Medical Center. So this is, of course, a demonstration of protocol, but in bulk diamonds. So it's not yet really relevant for biomedical imaging. For biomedical imaging, we need to transfer this all again to nanodiamonds, which can be taken as a marker for certain protein and then imaged in MRI scanner. So you need to repeat this all for diamond particles. And so example of this is shown in the next slide, where we hyperpolarized nanodiamonds and then measured them in a nuclear magnetic resonance spectrometer. We haven't done imaging yet, but we have been able to enhance the signal of NMR of diamond particles by a couple of orders of magnitude. So these particles now can be potentially applied for magnetic resonance imaging. I need to say that polarizing diamond particles is much more challenging because they have all different orientation. EPR spectrum is very broad, and some robust protocols like integrated solid effect or spin echoes need to be developed and applied for making this polarization transfer to be efficient. You can even enhance the signal further by enlarging number of carbon-13 nuclear spins inside of particles. When synthesizing diamond, you can modify your carbon source. And this work was done by Valery Davidov in Troitsk, the Institute of High Pressure of Russian Academy of Sciences, where he was able to produce nanodiamond with increased concentration of carbon-13. So here I should give you examples of NMR spectra of natural abundance, 1% carbon-13, then enhanced concentration, enhanced doping of diamond by carbon-13. And these particles can be even more kind of a sensitive tool for enhanced magnetic resonance imaging. So what we expect to get is essentially very high sensitivity of MRI in terms of detection of number of particles. We would like to compete in developing this tool with other molecular imaging methods like positron emission tomography. In PET, you can detect very small number of labels. Currently, MRI is not capable to do this, so you need a lot of nuclear spins to create signals in MRI. But now hyperpolarizing particles might bring you to sensitivity levels on a nano and sub-nanomolar level, which is then considered to be a standard for molecular imaging. We can think also not only apply nanodiamonds for imaging nanodiamonds themselves, we can also think about leaking polarization to outside liquids, and this can be then the universal tool for hyperpolarization of metabolic substances. And currently, we are working actually on developing these protocols for polarization transfer via diffusion of spins from or spin polarization from inside of diamond to outside. Usually, this diffusion is very slow if your nuclear spins are very rare. So in order to enhance the diffusion, we have created first nanodiamonds where the core containing NV center is natural abundance carbon-13, but the shell is highly doped up to 100% with carbon-13 nuclear spins. Remember, these nuclear spins are interacting with each other in this case, and polarization diffuses out from inside of nanodiamond to outside of nanodiamonds. So these core shell particles were created by Valery Davidov at High Pressure Institute of Russian Academy of Science by using a seed nanodiamonds having NV center that was commercially available Purion nanodiamonds, and then overgrowing it in high pressure, high temperature reactor using a carbon-13 enriched source, in this case, a naphthalene. And so this is a result of course shell particles. You see size of diamonds is larger, but also properties are different. So if you take Raman spectra of this diamond, so you will see a very significant part of Raman line to be associated with C13 enrichment. So this small part is a core. You can also see that NV center ODMR corresponds still to the core and normal ODMR, not related to strongly coupled carbon-13 spins. And the mass spectra of core shell particles are very broad because the spins in the shell are interacting, so that leads to this width, and this interaction is very essential then for spin diffusion and ability to polarize external spins. So ability to diffuse is also related to T1 time, relaxation time of nuclear spins. So there is a spin diffusion in a system, but if spins are interacting with other parasitic spins, for example, like P1 centers, they lose the polarization. And for a typical T1 relaxation time of nuclear spins on the order of a couple of minutes, the diffusion length of this wave of polarization is about 20 nanometers. So you need a shell to be less than 20 nanometers. If the layer is thicker, then the diffusion will be stopped by basically relaxation inside of these layers. It's also interesting that very long relaxation time, much longer than this 2 minutes, also have been observed, especially for diamonds with very low P1 concentration. Here I show you some recent results where we have studied a mixture of nano and micro diamonds. This mixture do have 2 components in relaxation time. The short component, possibly related to small particle, is about this 100 seconds. But the larger particles do have T1 relaxation time on the order of tens of minutes. So we can basically polarize nuclear spins inside of diamond in these particles, and its polarization will remain for tens of minutes, which provide a very interesting resource for this polarization diffusion, polarizing external spins, but also perhaps for imaging nanodiamonds inside of MRI markers. And last point I would like to mention, and it's that we are still right now relying and often in nanodiamonds that are having a random position of nitrogen. So you never know in diamond particles how many nitrogen are there, what is the distance between nitrogen and the surface. And so there is also effort in several research groups how actually to improve it by having a seeded growth, a bit similar to that I was showing before, where you start with small nanodiamonds and you overgrow the shell, and now replace the seed diamond particle by adamantane-like molecule, which is chemically synthesized, and introduce the precursor of a color center already inside of the structure of the molecule, and then overgrow it to a nanodiamonds. This is very challenging task because under normal condition of growth of diamond, these molecules will be destroyed, so the seed will be lost. And there are basically now efforts in finding condition, low temperature growth, where the adamantane molecules survive. So far, it was shown that you can grow nanodiamonds based on the adamantane seeds, but what still need to be shown that the seeds survive. So here on the right side, you see how the MR spectra of NV center inside of nanodiamonds grown from the adamantane or in the presence of adamantane. But the final confirmation that adamantane survived the overgrowth, this need to be done from my point of view. All right, with this, I think I conclude the presentation and just again give you an overview of today's lecture. So we have seen that single NV centers can be very promising sensors for bioscience and can be used for sensing biomolecules, but not only. It can be used for sensing processes, metabolic processes, action of the molecules, action of the membrane channels, measuring temperature at nanoscale. This is all come within reach, and also the new applications as MRI tracers. I think it's very important where you use optical polarization of NV center as a resource to polarize nuclear spins. So this is a main resource in MRI. So far, all the applications were explored at the level of, like single NV center. not so much exploring interaction between NV centers. And this is maybe what is interesting next step, whether we can combine NV centers in different nanodiamonds in ordered structures to make them interact, to create entanglement, and this can be a resource also for sensing, to make better magnetometer using entangled state. So with this, I think I conclude and would like to thank you for your attention.
Fedor, thank you very much for your very educational and very inspiring talk. So now it is time for questions. Please feel free to unmute yourself and ask your question. Or I can read also from chat your questions.
I think I also can read chat. Yeah, thank you.
So maybe start from chat. Fedor, what do you think?
Can you please stop sharing so we see each other? Thank you.
Thanks.
I know I always forget to do this too.
Right.
Yeah, and you can go to audio mode. We can enjoy more seeing faces of each other.
Right. Any questions?
So, hi, I'm Natalie Strakova, University of Colorado, and actually I'm an MRI person. I'm just wondering, I mean, C13 polarization is great, but it's not in the clinical environment, and it's predicted it has never been in the clinical environment for the next 20 years. Is it possible to do like xenon hyperpolarization instead of the C13? We don't have the channels for C13.
Yeah, I think it's a very important point. Yeah, maybe there are two sides of problems here with C13. One is that nanodiamonds themselves have a long way towards clinics, right? Because side effects in a body are not well studied, and only animal studies are underway. So basically, polarizing spins inside of diamond is more for preclinical studies, not for clinical. But now polarizing carbon-13 inside of diamond give you possibility potentially to polarize carbon-13 outside of diamond, and polarization on carbon-13 outside of diamond. So if you have it on a pyruvic acid or other molecule, that can be transferred also to hydrogen, to any other.
Perfect. Yes.
However, also carbon-13 is of interest. In many clinical scanners can operate using carbon-13, and there are also applications, especially for metabolic MRI, for carbon-13 NMR.
Of course, some, C13 pyruvate, like I was doing my postdoc at UCSF when we started doing C13 pyruvate, but in the clinical setup, it's no, we don't have C13 channel, we don't have C13 coils. This was my point. But it's for the future. Thank you.
It could be, and it could be also like from C13, you can swap to hydrogen, but then of course, the only point with hydrogen and hyperpolarization, the challenge that usually hyperpolarization on hydrogen don't live very long. So that's why C13 was so much explored, because molecules with hyperpolarized C13, they have pretty long T1. You have more time to image.
Yes.
But for hydrogen, you might be like limited in time. Yeah.
It's why we're using xenon. Okay, great. Thank you. Agree totally. Thank you.
Fedor, to follow up Natalie's question, what mode of hyperpolarization of nanodiamond labels in MRI are envisioned? Is it external hyperpolarization and then injection, or it is in vivo hyperpolarization?
It's a more hyperpolarization and then injection if you would like to image nanodiamonds, because this hyperpolarization requires very strong illumination. So it cannot be done, at least not in a straightforward way, in a body. So it needs to be hyperpolarized and injected. So if you polarize external liquids, then so you polarize nanodiamonds, and then polarization is transferred to liquids still outside of the body, and then liquid is injected inside of body. So it's always outside the body. So this hyperpolarization is kind of process that is hardly compatible with inside of clinical kind of regime operation.
Thank you. There is a question from Tom Delord. I might have missed it, but could the abnormally high P1 to NV conversion ratio in 25 nanometer nanodiamonds be caused by a depletion of the P1 center into a non-magnetic charge state?
Yeah, so our interpretation, so we are also surprised by this very high conversion. So maybe I remind, so the conversion was above 50%, reaching 60%, and usually you believe that you need two P1 centers at least to form one NV, one to form NV and another is to donate electron. So then in this regime, you cannot reach above 50%. So our interpretation was that our measurement of P1 was not the measurement of nitrogen content. So it's kind of, I think, what you call like presence in other forms. So maybe in part of our P1 centers, we got lost electrons. So it was form of nitrogen which is not measured by EPR, but still this nitrogen was still capable to build an V center. So in this case, you can pick up one nitrogen that was not active in EPR to form an V, and the other nitrogen can still donate an electron. That was our interpretation of this.
Yeah, thank you. It makes a lot of sense.
Yeah. So then the next question is, I would like to ask another question just to verify. In your ODMR sensing with nanodiamond particles, do you follow just one particle at a time, or it's ensemble of particles?
In our experiment, typically just one particle. It can be in some cases particle kind of sitting somewhere inside of cell, but not moving so much. In some cases, it's moving, and we have to track it by always kind of moving a laser focus to follow it. But it's always, in most of the cases in these experiments, it's one particle always like tracked. There are other possibilities with the CCD where you can measure many particles in parallel, and it has some advantages to be, faster and capable to see more inside. But this was more confocal microscope.
And what is your vision, say, for practical applications to move to, say, biomedical field when there will be biologists and users of the technology? Is it more for this CCD-based approach that should be considered?
Yeah, I think can be different modes. So it depends. Depend on the application. I think in sensing, and from my point of view, also in biology, there are so many scenarios that one always need to find the best sensing method. Like in optical microscopy, sometimes they use very complicated stats, super resolution. Sometimes they use very simple microscopy, depending on your application. So that's.
Thank you. I have a quick, maybe practical question. One thing that I was just thinking is like, the Earth's field is something like 50 microtesla. How does that affect measurements when you're trying to get below that? Because you cited measurements in the nanotesla. Like are there practical considerations or? Yeah.
Yeah, that's a very good point. So the Earth's field provides you always a bias. And so the sensitivity is defined by smallest measurable field. So we do see Earth's field. We usually even apply some more bias field to separate transitions. And then we try to measure the smallest possible signal on top of this. So actually, Earth field in a bias is not a very big deal. So it's a standard bias. And there, by the way, also some for bulk diamond, there are attempts to measure Earth field using small diamond magnetometers with very high precision. And because Earth field is kind of locally, it's very individual, there are also applications to use this as a GPS-free navigation. But that's another story. But in our case, so we are stationary. There is also bias, and there is basically on top we apply our bias to separate transition even more, and then we try to measure smallest measurable.
Yeah, that's a good point. Yeah, thank you.
Okay, please feel free to unmute yourself and ask your questions.
Hello, Fedor. Thank you very much for a very nice presentation. I may have a question which is a little bit outside of this agenda today, but hopefully it's okay. With your different methods of modification of nanodiamond surfaces, have you ever come across a necessity to make it hydrophobic, the surface?
Mm-hmm. Yeah, so we were always trying to make it hydrophilic to kind of being able to operate in biological environment. Mm-hmm. But I think that it might be applications, of course, also to have it hydrophobic, especially if you would like to sense, for example, NMR of external, not maybe in medical application, but to sense, for example, NMR of kind of liquids that not the kind of non-polar. And so that's can be in a sense, yeah, that's can be. So we are always trying to make it hydrophilic, but I think it can have applications.
Yeah, we have such applications. It's just we're trying to find something easier to make than fluorinate them.
Maybe fluorinated surfaces will make it hydrophobic, right? Or...
Yeah, it will. It's just too hard to do. I'm looking for the others.
Right.
Thank you.
I think that there are applications for incorporation, for example, into like the lipid bilayers or into neurons and things like there are specific.
Or maybe exactly in a cell membrane or so. Yeah. Maybe you can bring it and then measure electric fields across the membrane. That could be application.
That's the one that came to mind for me.
Yeah.
Mm-hmm.
Okay, thank you.
And we provide C18 functionalized fluorescent nanodiamonds, I believe 100 nanometers in size, but can be smaller.
Be interested, absolutely.
Mm-hmm. Fedor, very simple question. What is your favorite size for quantum sensing of nanodiamonds and what for MRI imaging?
Yeah, I think for all applications, ideal diamond can be for sensing application, like the smallest possible with in V center with long coherence time, but often these very small particles have shorter T2 time of in V center. And so currently typical use is maybe it's a few tens of nanometers. We do use small ones, so it goes inside of cells and so on, but not below 10 nanometers. So there are some ways to get very small particles even below 10 nanometers, but T2 time might be shorter, so its surface is very, very close. So in typical experiments, it's a few tens of nanometers.
Mm-hmm. And for MRI, probably
for MRI,
much, right?
For MRI, of course, ideally, you might like to have small particles. Maybe they are better released from the body. If you are thinking about preclinical applications, it's always not so good to inject large particles because they are not released. Mm-hmm. But on the other hand, surface might affect T1 time. And so we need certain T1 time to be able to inject and then after transport measure. And so we are basically trying out different sizes, and we do see that we polarize both, like submicron, so maybe a few hundreds of nanometers, but also a few tens of nanometers, and exploring hyperpolarization, all of them.
Okay. Any other questions? Then I would like to thank you, Fedor, again. It was a beautiful talk. Thank you so much.
Thank
And
you very
hope
much.
to see
Olga.
you at
Thanks for
some
joining,
conferences.
and, thank you for organizing lectures. That's really exciting events.
Okay, bye-bye.